Okay, so our data has come back. Let's review what that consists of. You should have an observation of pulsar 0329 plus 54. Each team should have one observation of 0329 plus 54. This is the brightest, easiest pulsar. It's almost always in its on state. Pulsars, sometimes they're on, sometimes they're off. Not all of these are guaranteed to work, but 0329 plus 54 almost always is in its on state. That said, I just did a class and we collected data and it was in the off state. So if your 0329 plus 54 analysis doesn't work, just resubmit your observation. Get some more 0329 plus 54 data, and it's almost guaranteed to be good the second time if it wasn't the first time. Okay, that's the primary thing. Then each teammate picked their own pulsar from a list in the module guide, and these are more challenging. And so each teammate should have their own data set, and half of these will work and half won't, because some of them will be in the off state with no pulses, and it'll be a bust, but some of them will work out. Okay? And each team should have one polarization calibration observation. This is where we did this loop-de-loop on not a pulsar, just an unpolarized source. And since we kept looping on it, off it, on it, off it, it looks like a pulsar in our data. But the key property here is it's an unpolarized source. We're going to use this to calibrate our polarization measuring capabilities. Okay, so that's what you should have. So let's get started. You go to Skynet, go to radio observing, find your 0329 plus 54, or maybe one of your teammates observed it and they've given you the link in the observation log. It should look like this. Click on it, we can see the preliminary data products. And in my case, I did have some RFI at the beginning here. This can mess up your observation, but maybe not. We'll see. But you can see here, 1381 megahertz. Someone was transmitting for the first 20 seconds or so of my observation, possibly messing it up, but we'll see. But looking at the rest of it, and even on top of it, I can see little pulses. See these little spikes in the upward direction? Those are pulses. And with most pulsars, these will be so faint you won't see them here. You may not see them at all. We have to pull them out statistically. But with this pulsar, you should see them. And I do. Okay, so go to continuum and down to calibrated. Not spectra calibrated, continuum calibrated. It's just a text file averaged over all the frequencies. And you're going to save it. I'm going to come out here and right-click, save link as, and we'll save it. And depending on your browser, it may ask you, do you want to keep this? The answer is yes. Okay, so I saved it. So now I'm going to go to our old plotting tool. And most of our analysis tools are in the Astromancer framework. We're still in the process of moving this one over in future years. This site may be retired, and you can just go to Astromancer and open up the Pulsar tool. We just don't have that ready yet, so I'm going to show you using the old tool. The URL is here, and we'll have the most recent tool linked in the module. Okay. Let's go down to Pulsar. And it starts by loading up just some random data. This is not your data, it's just random noise. Come down here to upload data file. I'm going to upload that file that I just downloaded from Skynet. Here I see it, and I see the pulses. See all these pulses in the upwards direction? We have a lot of noise, but we have pulses riding above that noise. That's great. Now, I should say, some of you may have RFI contamination. Now remember, in this data set, I had a lot of RFI at the beginning. I don't see it here because one thing that this does, it's not just plotting the light curve, but it's subtracting the background. It's figuring out the background, going through the data set and subtracting it on some time scale, starting with the 3-second background subtraction. If I increase this to something really big, I just did 30, may take a second to process, but yeah, you see it was not able to remove all my RFI in that case. But just by the process of background subtracting on reasonable timescales, it may remove your RFI, though it may not be perfect. You may have a little bit left over at the beginning of the RFI period, the end of the RFI period, and that can mess up the analysis to come. You may see a little like extra scatter, both on the positive and negative direction at the start and stop of the RFI period. Now, you can remove those. Just find out where it occurred. The first number there is the timestamp. Scroll down in your table to that timestamp and erase data both before and after. I'll just erase a big chunk to give an example of what this looks like. See how I cut out a little piece of the data here? Now hit Control Z and stick that back in because I don't have any problem on this data set. But if you do on yours, first thing you have to do is cut out that problem. Okay, but most data sets will be okay. I just mention it because occasionally you can be RFI contaminated. Now, before we analyze this, let's just sonify it. Let's see if we can hear the pulsar. Really hard. If I listen carefully, I think I heard a pulsation in all that noise, but it was really difficult to do. But by the end of this analysis, it will be really easy. We're going to clean this up. But always start, listen, see if you can hear it. Another thing you could do is you can zoom in. Here we see the individual pulses very well defined. And you can measure the period right off of this if the pulses are not below the noise. If they're below the noise, then in the next part, we'll try to extract it. But here, they're riding above the noise, so I can just measure. Let's find one that's easy to subtract. So this one, looking at it, it's at 90.845 seconds. The one before it's at 90.14 seconds. That's about 0.7. This thing's pulsating about once every 7/10 of a second. Just think about that. This is an object more massive than the sun, rotating faster than once a second. Pretty impressive, pretty extreme astrophysical scenario. Okay. So, next, let's go to the periodogram. Here, we were able to just measure it off the light curve, but we won't always be able to. So we'll go to the periodogram. We're going to compute. Okay. This is an algorithm. It's called Lom-Scargel. It goes through that time series that we were just looking at, looking for periodicities. And it can even find them if they're below the noise. To us, it may just look like noise, but if there's something in there pulsing, it can pick out the pulses. Now, this one was pretty easy. It found power on different periods. Here we have the period, and we see spikes at certain periods. So what all can be in here? You're normally looking for the rightmost, biggest spike, but not this noise out here. You'll always have some noise out here at high periods. We call that high period noise, and it's nothing real. But somewhere here, and I should say all the pulsars we're doing, their periods are between about 0.2 seconds and about 1.4. Okay, just to give you a hint, we're looking between 0.2 and 1.4. And here I see a pulsation around 0.7. We just measured it in the light curve, so good thing it's here. But what's this other stuff? 0.35, that's half of 0.7. These period finding algorithms find what we call overtones. So this is half the period, twice the frequency. Half of that is 0.17 and a bit. Half of that, about 0.09. And half of that, 0.05 perhaps. So we have the main signature, we have the first, second, third, and maybe, though it's not exactly in the right place, fourth overtones. So you get overtones. Don't get confused by the overtones. You want the base period out here on the right and not the overtones. They'll all be equally spaced on this logarithmic plot. Okay, so you don't want the overtones, you don't want the high period noise. You may see some other spikes like this right here. Something in this data is pulsing at 0.0649 seconds. Could be RFI. There could be some low-level RFI, and it has a little pulsation to it. It could be the detector electronics. The detector has electronics, and some of the components work on certain periods, and that can work its way in here. So this is kind of the trickiest part. It's easiest if you can just measure the period right off the light curve, which we were able to in this case. But you won't always be able to. Sometimes the pulsations will be below the noise, and you have to rely on the periodogram. Now, let me give you a tip. You can improve the periodogram. Once you've figured out the base frequency, in this case, it's around 0.7, go back to the light curve page and change the background subtraction scale to something that's just a little bit bigger. So we measured 0.7, let's try 0.8. That changes this data just a little bit. And when we come back to the periodogram page, press compute, we'll get a slightly different periodogram, slightly different Lomskargel spectrum. You see this spike has been enhanced, made stronger. The high period noise has been suppressed. Anything above that background subtraction scale, in this case 0.8 seconds, got suppressed. Just makes it easier to see. Okay, the next step is to measure this period accurately. There are only a couple points on this spike, so we want to zoom in so we can get a better measurement. It's around 0.715. So let's search from a start period of 0.7 to a stop period of 0.73. So zooming in on that spike, there it is. And again, we have two channels because we have two orthogonal rods, metal bars up in our detector. Each is detecting signal. And we put our cursor on the peak, 0.7145. The other one's 0.7145. And you really need to measure the period out to 4 decimal places. It's that accurate. So once we do this, we go to period folding. And the period here, we're going to enter that in, 0.7145. And what it's doing is it's taking the data set and it's chopping it up into pieces that are 0.7145 seconds long, piece after piece after piece. Then it translates each piece on top of the first one and averages them. And this will beat down the noise. The noise will cancel when you average, but the signal stays there and gets better defined. Now there's a slider here for phase that just shifts it. And this plot is showing 2 periods. If you turn this off, you see 1 period. You turn it on, you see 2 periods. It's traditional in a folded light curve, a period folded light curve, to show 2 periods. It's just the exact same data plotted twice. So if you look at the little variations, they match. It's just the same data plotted twice, but it's kind of easier to look at. You can see the repetition. Okay. Let's tweak this just to make sure. We measured 0.7145, but maybe it's 0.7146 or 0.7144. So I look at the peak here. It's almost at 3.5. I'm going to go up to 0.7146. That's less signal. So back to 0.7145. Let's try 0.7144. Less signal. So 0.7145. Just tune it up. Tweak that fourth decimal point, maximizing the signal. It gives you the best clipping and folding of the data that you can get. Now, let's listen to this. You remember what it sounded like originally. Very hard to hear the periodicity. That's very clean because we chopped it up, we folded, we averaged, we beat down the noise. And so you can really hear that. Every pulse you hear, that's a rotation of the neutron star. And you can save that sonification by pressing this button. Okay. Now, that's how you measure periods. But there's a whole nother part to this, and that's establishing that these are polarized. If they're polarized, that tells you it's not thermal emission, it's not bremsstrahlung, it's something to do with magnetic fields, such as synchrotron, or in the case of pulsars, curvature, which is very much related. Okay. Now, let me just remind you how that works. So here's a picture of our detector. You know, we have the dish, the radio waves bounce up the dish up to prime focus. Up there we have a detector. In that detector, it's fairly simple. I mean, there are complicated parts, but it boils down to something fairly simple. Two orthogonal metal rods of just the right length to detect this wavelength. And that's blue in this diagram. One up, one up, down, one left, right. Now, when the radio waves come in, some fraction of it will be unpolarized and detected by both rods. But some fraction will be polarized along a certain angle. Now, if that polarization aligns with either of the rods, you only detect that component in that rod. If the wave is oscillating up-down, we'll only detect it in the up-down rod. If it's oscillating left-right, we only detect it in the left-right rod. Most likely it's on some angle, in which case you'll detect some in one rod and some in a different rod. And unless it's on the 45 degrees, you'll detect different amounts in the two rods. Now, we talked about this before, but here at the cone of emission, the magnetic field is curving one way on one side and the other way on the other. So again, if I'm the pulsar and I'm sweeping by, first you get curvature this way, that's one polarization state. Then you get curvature this way, that's a different polarization state. So whatever the polarization was at the beginning of the pulse, it should be different at the end of the pulse. So you'll have different amounts in the two detectors. Even if it was on the 45 and you started with, say, equal amounts in both detectors, it will change by the end of the pulse and won't be equal. So we're going to try to detect that in our data. We won't always succeed. But if we do, it tells us that magnetic fields are indeed involved. I painted this story, but you could approach it from the other direction, look at the data and work our way back towards that story. Okay, so to see if it's polarized, first we press the show difference button. That's subtracting one channel from the other. And there appears to be a difference between the two channels. But we can't jump to conclusions. We can't assume that is polarization because these two channels may not be well calibrated to each other. There's a calibration slider here where we can multiply the second channel. You see we can make it larger or smaller. We need to know the right calibration to multiply that second channel so they're at the same level so they can be compared. So again, the way we do this is we look at an unpolarized pulsar. There is no such thing. So instead, we did a loop-de-loop over an unpolarized source. So let's look at that data. We're simulating an unpolarized pulsar. So to do this, let's open up a second instance of the tool so we don't lose all the work from the first instance. Okay. And I've already grabbed some of this loop-de-loop data, daisy data. Did a daisy on Cas A. We did 4 petals, 4 passes in 60 seconds. So the period of this pulsar, fake pulsar, should be about 15 seconds. Let's just set our background subtraction to 16, get a little bit above that. Okay. Going to go to the periodogram and let's search out to, let's say, 20 seconds. So here it is. It's pulsing once every 14.7. Again, it's not really pulsing. We're passing over this source every 14.7 seconds. These are the overtones. So we'll go to period folding and type in 14.7. Okay. And let's tweak that. 14.8 was a little bit lower. Yeah, 14.7. So now we're going to we can turn on show difference and then take the calibration and bring them into alignment. So you can either try to line up the red and blue points or minimize the difference. So I get 1.13. I need to multiply that second channel by 1.13 so it's at the same level as the first channel. Okay, now that we know this, we can use this for all of our pulsars, for 0329, +54, and all the others, as long as it was taken not too many days apart from this polarization calibration observation. Okay, so we used our fake unpolarized pulsar to set the calibration. Let's go back and set that to 0.13, 1.13. Okay, so now the 2 channels are calibrated, and indeed with the difference, we see a signature. If we zoom in here, basically the one, we're detecting more in one channel and it's leading the other. So we get this bump here. So that's telling us that it's polarized and hence magnetically field driven. This is curvature radiation, not something like thermal. Okay. So you're going to do this with all of your pulsars, but I just want to give you just some final reminders here. They're not all going to be turned on. Some will be on, some will be off. And you may not have a strong signature or any signature. If it's off, it's a bust, and just move on to the next pulsar. Now, let's go back to the light curve page here. Again, just a few reminders. Here we saw individual pulses. With these other tougher pulsars, you may not see individual pulses. It may all be in the noise, but just because you see noise doesn't mean there's nothing there. Move on to the periodogram. Maybe Lom-Scargill will pick something out of the noise. I'll reset this. On this page, don't be fooled by high period noise, by overtones, by RFI, by detector electronics. You got to find that base pulse, that base period. I think here I have one that's a little bit more challenging. Yours may look a little bit more like this. A lot of high period noise. This particular one, that is the pulsation, around 1/4 of a second. Again, we can go back to the light curve page. I do see some pulses in there. 1/4 of a second, let's do 0.3 as the background subtraction. Go back to the periodogram, recompute. Much better. So, if you can find it, then go back. Don't forget to do that. Change the background subtraction scale, come back, recompute the periodogram, and it should be a lot better. But you see, there's all sorts of other things. Some of these are overtones and RFI and detector electronic signatures. And so it can be a little bit tricky. Sometimes if you observe, say, more than 3 minutes and collect a lot of data, it increases your ability to detect this. That's something you can do. If you don't see it, you can go back, collect more data, say 3 minutes, maybe 10 minutes. But sometimes if you have a lot of data, these pulses get so narrow, you don't see them. So what you could do in that case is increase the number of points. It takes much longer to calculate the periodogram. Like if you have a pulsation signature and you don't see it in the periodogram, it may be so well defined it's less than 1 bin, and you have to add some bins to find it. On the period folding page, put the period back in here. Oh, wrong event. Let me come over here. Period folding, put the period back in here, 0.745. My reminder here is to sonify it. Sonify the before, sonify the after. Listen to this thing. There's one pulsar that's pulsing so fast, faster than a quarter second, that we just don't have enough bins across the pulse. And it will look messed up like this. This is pulsar 0929 plus 10. So if you're doing that pulsar, it's the fastest in our set. To make it work, you're going to have to decrease the number of bins. So instead of 100 bins, try 10 bins. Not as much resolution, but you can definitely see the signature here. And it's polarized. Okay. In this data set, you may or may not detect it in yours. Then, as you're doing this, there's a spreadsheet. It'll be linked in the module guide, or your instructor will provide it. I just did this with my students today, so here are my student teams. Here's 0329 plus 54. They all detected it. You can see their measured periods, and they also marked, most of them saw polarization. And then here are the 5 other pulsars, and you can see which ones different teammates did. This time we had a lot of luck with 2021 plus 51. Everyone detected it and the polarization. And we had luck with some of the fast ones, 0950, 0929. We had detections, polarizations, though a couple of them we struck out. With 1133 plus 16, 1919 plus 21, we didn't detect anything. 1919 plus 21 is a famous pulsar. That was the first one detected by Jocelyn Bell, for which her advisor got the Nobel Prize. Different times. Hopefully things are better now. That should not occur. Anyway, last bits of information is as you produce these, you're going to want to save the graphs. And before you do that, you'll want to give it a good title, good axis labels, and that's all in the module. If you go to the module guide, here's an example of a good title, axis labels. So, make sure you have good labels on there before you save the graph. And also remember to save your sonification. You'll use those in your blogs. Okay, that's how you do the analysis. Good luck. And that's it for this video.